Hello everyone, in this video we're going to see how to implement power function using both recursive approach as well as iterative approach. First we'll discuss how to implement it using recursive approach. Following that we'll see the iterative way. I must say both of these approaches are based on the same formula which we have learned during our primary school, that is a power x into a power y equal to a power x plus y. I hope you are well aware of this formula. Let us see an example. Consider 2 power 8. As per the above formula, I can rewrite this 2 power 8 as 2 power 4 into 2 power 4, right? Here, I can treat this 4 as x and this 4 as y. When I do this, a power x plus y, I will get 2 power 8, correct? That means we have divided this problem into multiple subproblems. Again, we'll consider this as a problem and divide this into multiple subproblems. Again, we'll consider this as another problem and we'll divide this into another subproblem. And so on till we reach 2 power 0 into 2 power 1. Okay? All of these are based on above formula. Okay, now tell me when we use recursion. We use recursion when there is a scope of dividing the given problem into multiple subproblems. Correct? So, if you see this problem, we have divided the given problem into multiple subproblems, correct? So it is very clear that we can use recursion to solve this problem. Okay? Now let's see how we can use recursion to solve this. Before we implement pseudocode using recursion, let's solve this first. Okay? So here we have divided the given problem into multiple subproblems, correct? Now let's try to solve each and every subproblem and then trace back to the main problem. Okay? Now if you see here, the last subproblem 2 power 1. We know 2 power 0 mean anything power 0 it is 1, correct? And anything power 1 it is the same value, correct? That means we'll get 1 into 2 we'll get 2. So what is the result of 2 power 1? It is 2, right? So it is 2 into 2, which means 4. So what is the result of 2 square? It is 4, right? That is 4 into 4. That implies 16. So what is the result of 2 power 4? That is 16, right? So we can directly replace 2 power 4 as 16 into 16. That is 256. Correct? So this is how we finally get the answer by dividing this problem into multiple subproblems. Okay? Now let's write a pseudocode for this. Okay? Here I am writing a function that is pow, which accepts two parameters, that is a comma y, and returns an integer value, that is final value after calculating the power. Here a is the base value and y is power. For example, if I have 2 power 8, then a equal to 2 and y equal to 8. Now if you see the above problem, we have divided the given problem into multiple subproblems, right? So based on that, what we can do here is that we can just divide the given problem into multiple subproblems. So we can return as power of a comma y by 2 into power of a comma y by 2. Again this will be treated as another problem and again this will be treated as another problem. Okay? Now let's do a quick dry run of this program. Let's consider 2 power 8. Okay? 2 power 8 we can write it as power of 2 comma 8 by 2, that is 4 into power of 2 comma 4, correct? which means 2 power 4 into 2 power 4, that is equal to 2 power 8. We're getting 2 power 8, so no issues. Now let's check for 2 power 7. Okay, 2 power 7, we can write it as power of 7 by 2, that is 3.5, that is 3, into power of 2 comma 3. That means 2 cube into 2 cube, that is 2 power 6. Which is not expected, right? We are not expecting 2 power 6 here. We are expecting 2 power 7. So for odd cases, for odd powers, this implementation is not working. So we need to handle odd powers separately. So for that, I need to write one condition here. So if y mod 2 is equal to 0, return this. Else, return power of a comma y by 2 into power of a comma y by 2 into a. Okay, correct? So here 2 cube into 2 cube into 2, that is 2 power 7. So we are handling odd cases as well. That's it. Now one thing is left, that is base condition. If you see here, when we are stopping it, when we see 2 power 0, because we know its result, anything power 0 is 1. So our base condition will be if y is equal to 0, return 1, because anything power 0 will be 1. That's it. So we have implemented power function using recursion. Now let's do a quick dry run of this program. Let me draw a recursion tree for that. Consider 2 power 5. Okay, so here initially it will be power of 2 comma 5. This is the initial input. Here the power is odd, correct? So when the power is odd, what we are doing? We are just dividing by 2 and into the actual value, correct? That is, we'll get 2 comma 2, 2 comma 2 and 2, correct? So it will be divided into 2 comma 2 and power of 2 comma 2, and this will be multiplied by 2, correct? And again power of 2 comma 2 will be again divided into power of 2 comma 1, power of 2 comma 1. This is even power, right? So again we will not multiply with a. Again this will be divided into power of 2 comma 1 to power of 2 comma 1, correct? Again this will be divided into power of 2 comma 0 and 2 comma 0, and this again will be 2 comma 0, 2 comma 0 and so on. Okay, now if you see here, what is our base condition? Our base condition is if y is equal to 0, return 1, correct? So here y is 0 here. So when y is 0, we'll just return 1 from here. That is, we'll return 1 here. Again y is 0 here and we'll return 1 from here as well. So 1. So what we'll do, we're just multiplying it here. So 1 into 1, that is 1, correct? If you see here, when the power is odd, what we are doing, we are multiplying with 2, right? And again we are multiplying with 2 here, correct? So what we'll do, 1 into 1 is 1, 1 into 2 is 2. So we'll return 2 here. And again here we'll return 2 from here. Okay. Now 2 into 2, that is 4. So we'll return 4 here. Okay. Similarly here also we'll return 1, and here we'll return 1 and we'll return 1. Okay. Here also we'll return 2, sorry, and again we'll return 2 here and we'll return 4 here. Okay. And finally we'll multiply 4 into 4, that is equal to 16. 16 into 2, that is 32. So this is our output. Okay, hope you got this. Now let us see the time complexity of this program. Now let's analyze each and every statement separately first. Okay, it will be easy to calculate time complexity if you do in that way. Now what is the time complexity of this statement? This is big O of, this is time complexity of 1, correct? What is the time complexity of this statement? This is TC of n by 2. Let's assume here y as n, okay? TC of n by 2 plus TC of n by 2, correct? And here we have again TC of n by 2 plus TC of n by 2 plus TC of 1, correct? So if you consolidate all of these together, we'll get, if I assume this total time complexity as TC of n, that is TC of 1 plus TC of n by 2 plus TC of n by 2. This is the total time complexity, okay? If you notice here, either this or this is getting executed. Both are not getting executed at the same time, right? So we can write either one of them, correct? That's why I wrote TC of n by 2 plus TC of n by 2. And this is the first one, TC of 1. Okay. Now, TC of n by 2 plus TC of n by 2, that is 2 into TC of n by 2 plus TC of 1. That is big O of n. So time complexity is big O of n. So time complexity of this algorithm is big O of n. Now how to optimize this? To do that, let's have a small observation on the recursion. If you see here, you are calculating the power for 2, 2, correct? 2 square, we are calculating the power here. And as part of that, we draw this recursion tree, correct? This recursion tree we draw as part of that. Again, if you see, we are again calculating the power for 2, 2. This is a duplicate, right? This is duplicate operation. Here we are calculating the power once, but again we are doing it. This is duplicate, right? So we can optimize this. We can use the same result here as well, correct? So how can we do that? Let's see. Let me copy this program. Okay. Here, instead of calculating power twice, what we can do is that we can calculate once and we can store it in some temporary variable and we can use it here as well, correct? Let's see how to do that. First, I'm going to calculate power here. That is int some temporary variable equal to power of a comma y by 2. Okay. And here, instead of calling the power function, I'll call temp into temp. Okay. Here as well, instead of calling this, I'll call temp into a, correct? That's it. Now let us calculate the time complexity of this program. Okay. So what is the time complexity of this? This is TC of 1, correct? So what is the time complexity of this? This is TC of n by 2, correct? This is TC of 1 because multiplication operation will be having big O of 1 operation, okay? And this is also TC of 1 because this is also having big O of 1 time complexity. Now if you consolidate this, what you will get? You get TC of n equal to TC of 1 plus TC of n by 2, correct? That is TC of n by 2, you can write it as log base to n. So we optimized it to log n. Why I wrote log n here? In each and every iteration, when the given input is reducing half of the times, then it will be log n time complexity. Okay, you need to remember this. So finally, we optimized this program to log n time complexity. This is how we implement power function using recursion. That's it. Now let us see how to implement power function using iterative manner. Okay. Even the iterative approach is also based on the formula which we have discussed earlier, that is a power x into a power y equal to a power x plus y. We know that we can form any number with sum of distinctive powers of 2. Correct? For example, let's say I have 9. So we can form 9 as 2 power 0 plus 2 cube. Correct? That's what it means. So we can form any number with sum of distinctive powers of 2. Correct? These both the powers are different. And we can form 9 with 2 power 0 and 2 cube. Now, if we write this 9 in binary representation, how does it look like? That is 1 0 0 1. Correct? That is 2 power 0, 2 power 1, 2 square and 2 cube. Correct? 2 power 0 plus 2 cube will form 9. Now, I would like to find the result of 3 power 9. Okay? So, as per the above statement, we can rewrite 3 power 9 as 3 power 8 into 3 power 1. That is the set bits in the 9. This is 1, 2, 4 and 8. So 3 power 1 into 3 power 8 will give 3 power 9. So if you just multiply 3 power the value of set bits, you will get the actual result, that is 3 power 9. Now the biggest question here is that how will you get the value of 3 power 8 here? If you closely observe, 3 power 8 is nothing but 3 power 4 into 3 power 4, right? Which is this value, correct? That is, if you multiply this value by itself, you will get this value, correct? Similarly, if you multiply the 3 power of this value by itself, you will get this value, correct? So what we understood from this value is nothing but the multiplication of previous value by itself. Understood? Which means 3 power 4 is nothing but 3 square into 3 square. And 3 square is nothing but 3 power 1 into 3 power 1. Okay? Now let's see how we implement a pseudocode for this. Consider the function name is pow. Similar like above, it accepts two parameters a, n. Let us consider we have to find the value of 3 power 11. A equal to 3 and n equal to 11. The binary representation of 11, 1, 0, 1, 1. And their positions is 2 power 0, 2 power 1, 2 square, 2 cube. So as we discussed here, we'll get final result if we just multiply a power set bits of n, correct? That is, here a is 3, that is 3 power set bits of n. Set bits of n is 1, 2 and 8, correct? That is 3 power 1 into 3 square into 3 power 8 will give us the final result, that is 3 power 11. So what we have to do? We have to find the value of a power each set bit and multiply them together to get the final result. Now what I will do is, I will just iterate towards all the bits of n and check if any bit is set or not. If any bit is set, then I will store the value of a power current bit multiplied by all previous bits. For example, at this position, the result will be having 3 power 1. And at this position, result will have 3 power 1 into 3 square. At this position, result will be storing 3 power 1 into 3 square into 3 power 8. That implies 3 power 11. Finally, when we reach the last bit position, we'll get the final result, that is 3 power 11. Let us see how to implement a pseudocode for this. To show these values, I'm going to take a variable that is result. By default, it will be initialized with 1 because when we're at this position, we don't have anything previous to multiply it with the current value. That is the reason why I'm taking the previous value as 1. And I'm going to take one more variable, that is temp. So by default, temp will be having a because we use temp to store the value of current position. For example, at this position temp will be holding a, and at this position temp will be holding a square, and at this position temp will be holding a power 4. Similarly, at this position it will be a power 8. So by default temp will be storing a, because when we are at this position temp should hold a, right? Now to iterate over each bit, what I can do is I'll just right shift each bit by 1, and if I get the first bit, then I can eventually read all the bits, right? For that, what I'll do is I'll write this condition, that is while n greater than 0, which means when we do right shift 4 times, which means the value will become 0. So at that time we don't have any bits to process, so we need to exit at that time. That is the reason why I wrote n greater than 0. Now as I told, if the bit is set, then what we'll do, we'll just multiply the current value with previous set bits value, correct? Which means result equal to, let me erase this, result into temp, correct? Here temp holds the current value and the result holds the previous set bits value. Okay, that's it. Here after this we need to update the temp value, because as I told, we use temp to store the current value of given position. For example, when we are at this position, to get the current value of this position, we need to multiply the previous value by itself, correct? So we have the previous value of this position in temp. So if we multiply the temp by itself, then we'll get the current value of next position, correct? That's the reason why we have to do temp equal to temp into temp. So this will give the current value of next position. After this we need to do right shift 1 time of n. Finally return the result. That's it. We have implemented power function using iterative approach. Now let us do a quick dry run of this program. Okay. Consider 3 power 9. Okay. So initially result will be having 1 and temp will have 3. What is the binary representation of 9? It is 1001. Correct. Just checking whether n is greater than 0 or not. Yes, n is greater than 0, that is 9 is greater than 0. And we're checking if the first bit is set or not. Yes, here the first bit is set. When first bit is set, we're calculating result as result into temp. Here 1 into 3, that is 3. And then we're updating temp as temp into temp, that is 3 into 3, that is 3 square. And we're updating n as n right shift 1, that is 9 by 2, which means 4. That's it. We have done one iteration. Now what is the value of n? It is 4. The binary representation of 4 is 100. Now n is greater than 0, right? What is the first bit in n? It is not set. So when the bit is not set, what we'll do? We'll just update temp as temp into temp. So the temp value is 3 square, that is 3 square into 3 square, that equal to 3 power 4. And we'll just update n as n right shift 1 times, which means 2. Now n is 2. What is the binary representation of 2? It is 1, 0. Correct? Is the first bit set? No, first bit is not set. So again we'll update temp with temp into temp. What is the previous temp? Previous temp is 3 power 4. That is 3 power 4 into 3 power 4. That equal to 3 power 8. And again we'll update n with n right shift 1 times. That is, now n becomes 1. What is the binary representation of 1? It is 1. Is the first bit set now? Yes, the first bit is set. When the first bit is set, what we'll do? We'll update result with result into temp. So what is the previous result? Previous result is 3. Correct? 3 into, what is the temp value now? Temp is 3 power 8, which is nothing but 3 power 9. And what is the temp? Temp now will become 3 power 8 into 3 power 8, which is 3 power 16. That's it. Now n becomes 0. At this point, our while loop will exit, because n is 0 now. Finally, what we are doing, we are just returning result. See, we got 3 power 9 in the result. That's it. This is how we implemented power using iterative approach. Now let us quickly calculate the time complexity of this program. Okay? Here, the while loop runs till n becomes 0. And at this point, we are updating n value. That is, in each and every iteration, n becomes half. So in how many iterations n becomes 0? Which is nothing but log n iterations. As I told earlier, if the given input is being reduced to half at each and every iteration, then the time complexity will be log n. That's it. I hope you have now understood how to implement power function using both recursion as well as iterative approach. Thank you for listening to my video. See you later in the next session.